Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from DeepSeek AI, DeepSeek v3.2, Efficient Long Context Reasoning and Agentic LLMs. Over the last couple of years, large language models have gotten dramatically better at hard, verifiable tasks like math, coding, and complex reasoning. But there's a problem. The best proprietary models are pulling away from the open source community. They're faster, more capable, and better at acting as real agents in tools and environments. DeepSeek v3.2 is designed to attack this gap head-on by combining efficient architecture, serious post-training compute, and large-scale agent training while staying open. The authors identify three main reasons open models struggle on complex tasks. First, most still rely on standard attention, which scales poorly with long sequences and makes both training and inference expensive. Second, open models usually invest only a tiny fraction of compute into post-training, so they never fully unlock their potential on hard reasoning tasks. Third, when you put these models into real agent settings, like browsing coding with tools or multi-step workflows, they often fail to generalize or follow instructions robustly. DeepSeek v3.2 is built specifically to tackle each of these pain points. DeepSeek v3.2 is more than just a bigger model. It introduces a new attention mechanism called DeepSeek Sparse Attention, or DSA, to make long context processing much cheaper. On top of that, the team invests heavily in reinforcement learning post-training, over 10% of the original pre-training compute, which is unusually high for open models. To make the model truly agentic, they build a large-scale pipeline that synthesizes tool use and agent tasks at scale. And finally, they push a high compute variant, DeepSeek v3.2 Special, which is tuned to compete directly with the strongest proprietary systems. In terms of raw capability, DeepSeek v3.2 is not just catching up, it's competing at the very top. On a range of reasoning benchmarks, the base system performs on par with GPT-5. The high compute Special variant actually surpasses GPT-5 on several fronts, and its reasoning ability is comparable to Gemini 3.0 Pro. Perhaps the most striking result is that DeepSeek v3.2 Special achieved gold medal level performance in both the 2025 International Mathematical Olympiad and the International Olympiad in Informatics, competitions designed for the world's best human problem solvers. At the heart of DeepSeek v3.2 is DeepSeek Sparse Attention. Instead of attending to every token in the sequence, DSA uses an indexer to select only the most relevant key-value pairs for each query, essentially a top K selection. This dramatically reduces the cost of attention, especially when contexts get very long. The key result is that you keep the benefits of long context reasoning, but with much lower compute and memory overhead, making both training and deployment far more scalable. DSA doesn't live in isolation. It's instantiated inside a multi-head latent attention framework, which can operate in both standard multi-head attention mode and a more efficient multi-query attention mode. This design lets the model train with a rich, expressive attention pattern, then switch to a more efficient decoding mode at inference time. The combination of MLA and DSA gives DeepSeek v3.2 both stability during training and speed during deployment, especially for long, tool-heavy conversations. A major differentiator of DeepSeek v3.2 is how seriously it treats reinforcement learning post-training. Instead of a small RL fine-tune, the authors design a robust RL protocol and allocate more than 10% of the original pre-training compute to it. This is a huge investment by open-source standards. The RL stage focuses on hard, verifiable tasks like math, coding, and structured reasoning, so the model learns not just to sound good, but to be correct and reliable on challenging problems. On top of the base DeepSeek v3.2, the team trains a high-compute variant called DeepSeek v3.2 Speciale. This version receives additional reinforcement learning and targeted tuning for extremely hard reasoning tasks, especially in mathematics and programming. The payoff is clear. Speciale ranks second in the 2025 ICPC World Finals and 10th in the 2025 IOI, competing directly with elite human teams. These results show that open models, with enough compute and the right training recipe, can reach world-class problem-solving performance. Reasoning alone isn't enough for real-world deployment. Models need to act as agents, calling tools, browsing, coding, and adapting to messy instructions. To train this, the authors build a large-scale synthetic pipeline that automatically generates agent tasks across many environments. These tasks include different tools, interaction patterns, and prompt styles. By training on this synthetic agent data, DeepSeek v3.2 becomes much better at generalizing to new tools and following complex instructions in interactive settings. A subtle but important design choice is how the model handles its own reasoning when using tools. DeepSeek v3.2 includes a thinking retention mechanism. Instead of discarding its internal chain of thought between tool calls, it preserves and reuses that information. This helps the agent stay consistent across multiple steps, reduces errors from context loss, and makes long, multi-step workflows more reliable. It's a key ingredient for stable, high-quality tool use in complex environments. When you line DeepSeek v3.2 up against both open and closed models that support thinking in tool use, it performs extremely well. Across math, coding, and agent benchmarks, it often matches or exceeds the best open models and comes close to, or even surpasses, leading proprietary systems in several categories. The comparison is especially meaningful because the authors focus on models that actually support chain of thought and tool integration, making it a fair test of real agentic capability. All of this capability would be less useful if the model were too expensive to run. The paper shows that DeepSeek v3.2, thanks to DSA and its attention design, is significantly more efficient than the earlier DeepSeek v3.1 Terminus on H800 GPU clusters. This means you can handle long contexts and heavy tool use without exploding inference costs. For real-world deployments like coding assistants, research copilots, or autonomous agents, this efficiency is crucial. One of the most interesting aspects of the work is that the reinforcement learning for agent behavior is driven entirely by synthetic data. Instead of relying on massive proprietary human interaction logs, the authors generate their own agent tasks and feedback signals. Despite this, the resulting model performs strongly on real-world agent benchmarks. This suggests that with the right design, synthetic RL can be a powerful and scalable path for open-source agent training. To stress-test agentic browsing, the authors evaluate DeepSeek v3.2 on BrowseComp, a benchmark that requires web navigation and information synthesis. They experiment with different ways of expanding compute at test time, like allowing longer reasoning chains or more tool calls, and show that smart context management can significantly improve results. This highlights that performance isn't just about the base model. How you allocate compute during inference also matters. DeepSeek v3.2 can run in a non-thinking mode where it answers directly, or in a thinking mode where it generates explicit reasoning chains. The thinking mode typically uses more tokens, but it also delivers higher accuracy on terminal-based coding and reasoning benchmarks. This trade-off between token cost and reliability is central to modern reasoning models, and the paper quantifies how much extra performance you gain by letting the model think out loud. Despite its impressive results, DeepSeek v3.2 is not perfect. Because it uses fewer total training flops than the very largest proprietary models, its breadth of world knowledge is still narrower. It also tends to require longer reasoning traces, more tokens, to reach the same answer quality as models like Gemini 3.0 Pro, which hurts token efficiency. And on the very hardest tasks, it still trails the absolute frontier. The authors are clear that closing these gaps will require more pre-training compute and further refinement of both the base model and the post-training recipe. Putting it all together, DeepSeek v3.2 shows a concrete path for open-source models to compete with the strongest proprietary systems. DeepSeek's sparse attention makes long-context reasoning affordable. A serious investment in reinforcement learning post-training pushes performance into GPT-5 territory. Large-scale synthetic agent pipelines give the model robust tool use and instruction-following abilities, and the Special variant proves that, with enough compute and the right training design, open models can reach gold medal performance in elite math and programming contests. The gap with closed models isn't gone yet, but this work shows it can be narrowed in a principled, open way.